In this video, we'll be once again covering increasing and decreasing of a function using function analysis or derivative analysis. In this example, we're going to be going ahead and covering f of x equaling to x squared over 4x plus 4. Now, one thing I'm going to note about this is what is the domain of this function? The domain of this function is negative infinity to 0, union with 0 to, negative 1. And from negative 1 to infinity. Again, that can be identified by setting the denominator equal to 0 and solving, giving us again that negative 1 is a value that is not in the domain of the original function. That means that if we have negative 1 as a possibility in the derivative function, then we should automatically remove it from being considered. Okay? So my next step here is taking the derivative. Again, taking the derivative, identifying where it is positive or negative will tell me where the original function is increasing or decreasing. Now keep in mind, be very careful with this. This is nothing more than a quotient rule that we're going to have to apply. So the derivative of the top is 2x, leaving the bottom as it is. Don't forget the quotient rule has a minus sign instead of a plus sign of the derivative of the bottom, which is 4 times the top, left unchanged. This is all divided by the bottom squared, so 4x plus 4 squared. Now, I need to, again, do two things. I need to find my critical points for this, which is the two things where the function is dne or where it's equal to 0. Those are my two cases that I've got to identify. Where is the critical points? They are going to be where the derivative does not exist or the derivative is equal to 0. So I'm going to go ahead and clean this up a little bit to make it easier for me to actually identify those points. Distributing this 2x first, combining the negative 4x squared all together, and I'm not going to, again, ever touch this denominator in terms of trying to simplify it down. We can, it'll just make things more complicated later on. So now I'm going to end up with what looks like 4x squared plus 8x on top divided by 4x plus 4 squared on the bottom. Now again, with this I'm going to have two cases. Where does the derivative not exist, or where does the derivative equal to 0? And because it is most common that students forget the does not exist case, I'm going to do that one first. So where is f prime not existing? Okay, that is where in this function right here we have radicals, logs, or in this case a rational function where the denominator cannot equal to 0. So I'm going to go ahead and set that denominator directly equal to 0. Doing so will tell me where I am not going to have a derivative function existing. So if I go ahead and solve this, I'll square root both sides, getting 0 equals to 4x plus 4. And therefore x is equal to a negative 1. So that is a critical point. You'll notice that that critical point actually matches up with the domain value that we had an issue with in the beginning. That's okay, it's not a problem. It is still a critical point, and it is still a location where the derivative might change from positive to negative or negative to positive. My next detail is going ahead and, again, second is f prime of x equaling to 0. In which case I'm going to set this whole function equal to 0. But if I do so, really the bottom isn't important. What's important is where the top equals to 0. So that means where is the top equaling to 0? 4x squared plus 8x equals to 0. I will go ahead and factor to solve this, factoring out a 4 and an x, giving me x plus 2. And therefore this case gives me x equals to 0. And this one gives me x equals to negative 2. So that provides me with actually 3 different critical points. I'm going to do the same thing I did in the last example, and that set up myself a number line. Starting at the most negative point is negative 2, going to negative 1, going to 0, and then creating my, again, number line test is what we sometimes call this, where I'm going to have a test value. Okay, that test value is going to be somewhere in the interval here, 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 and I'm going to identify those intervals up top here just to make it clear. I'm going to go from negative infinity to negative 2. My next interval is from negative 2 to negative 1. My next interval is from negative 1 to 0. And my last one is from 0 to infinity. Again, this should make sense based on simply taking a value from negative infinity to positive infinity and splitting up that interval from negative 2 to negative 1 to 0. So, my test intervals, my test values that I'm going to pick. Between negative infinity and negative 2, what is the value that sits in that interval? Well, negative 3 seems like it's going to be the smallest value that sits in that interval. Again, I could pick other numbers, but negative 3 just seems like the most appropriate one at this time. Here, I'm going to pick negative 1.5, because again, it is a value between negative 2 and negative 1. Again, I could pick something like, say, negative 1.1. I could say pick negative 1.9. I'm just going to pick negative 1.5. That is the same thing as negative 3 halves, in case I need to play with the fractions. Here I'm going to pick a negative 0.5, again somewhere between negative 1 and 0, and then over here I'll simply go ahead and just pick 1. So these are the test values that are in those intervals and I'm going to plug those test values not into the original, but into the derivative, because I want to know what is the derivative doing in those values, in those intervals. Okay, so I'm going to scroll down here so I can see the derivative function right here very clearly. Now you'll notice on the bottom it's 4x plus 4 squared, which means that this entire thing on the bottom will always be a positive number. That's going to be very important for us to evaluate whatever it is we're going to evaluate. Again, this bottom number right here is always positive. All that's going to matter is what happens at this top. So when I plug in -3, -3 squared is 9. I'm going to actually go ahead and write that scrap work over here. It's going to be 4 times 9 plus 8 times the -3. It's actually not terribly important what the number is. What's terribly important is it positive or negative. This ends up being 36, and this ends up being -24, so it looks like the top number for a -3 value is actually going to be positive. So in this case, it's going to be a positive divided by a positive, which is therefore positive. Again, we can double check this by using the factored form of this. If you look right here at 4x and x plus 2, you'll notice if I plug in -3 here, this term is negative. If I plug in -3 this one, this term is negative. Negative times negative is positive, divided by, again, an always positive number is positive. Now if I plug in -1.5, again, same concept. I'm plugging it into the derivative function right here. I can go ahead and plug it into the simplified form on top and the simplified form on the bottom, but the bottom is always going to be positive. So when I plug in -1.5 here, I get a positive number. When I plug in -1.5 here, I get a negative number. Negative times positive is negative, divided by a positive is always negative. So that's going to be a negative term. Now -0.5, this is going to be negative, this is going to be positive, and again, it's going to revert back to a negative. If I plug in 1, that's going to be positive, positive, and positive. So there I get another positive value. In which case, based on looking at this one more time, the original function, again, I don't care what it's actually going to look like, I just care that if the derivative is positive, the original function is considered increasing in that range. If the derivative is negative, we have decreasing, decreasing, and increasing. So this should provide me with enough information that you understand what's going on. Just to be clear, it is increasing on the intervals from -infinity to -2, that's this here. It is increasing on the interval from 0 to infinity, that's that one there. And then it is decreasing. Now be very careful on this decreasing case. Just because it's decreasing from -2 to -1 and -1 to 0 does not mean it's decreasing at -1. Remember, all the way back in the beginning of this problem, we identified that the domain didn't include that -1. Well, why is it in this? It's in this because it's still a critical point of this function, and it could have still changed from positive to negative in terms of the derivative here. So it is decreasing not from -2 to 0, it is decreasing from -2 to -1, and -1 to 0. And again, at that location, at -1, it's not doing anything. And that's the answer to that problem.